Log on, tune in, find out. Another good idea from Cambridge.
May I start with the usual reminder to please switch off the mobile phones. And now this session is the final one in our stream on choice experiments, and I hope it will round up the picture with some applications. And our first speaker is Emily Langser from Monash University in Melbourne.
Okay. And thank you for the invitation to the workshop and to present. So, I guess this is a bit of a change in pace in that today we're going to look at some applications of designs in health economics. So I'm going to be talking about the use of alternative specific designs in a particular setting, looking at preferences for drinking water. To start with some acknowledgements, was partly funded by the ESRC, MRC, NIHR, but also to acknowledge folk who are also involved in this study, particularly Jordan, who's here, but also Cam Donaldson and Mike Jones-Lee. Okay, so by way of overview, I'll start with, I guess, some motivation for why, at least in health economics, we might want to think about the relationship between experimental design and indirect utility functions and why that might be important. Then give a brief overview of the type of design that I'm going to use or have used in the study. I'll then spend a little bit of time talking about the method of data collection, best-worst choice experiments, because it's slightly different to a standard choice experiment. So I'll talk about that, and then about one particular way to analyse that data that I use in this study. And I'll then get onto the empirical example to demonstrate these various methods. Okay, so as I think you'll know, and we had a great introduction to this yesterday, choice experiments, the way I think about them at least, is that they combine three key things. First of all is obviously experiments, what we're all interested in here today. So the use of experiments to generate the choice data. Then once we have the choice data, we use that to estimate indirect utility functions. And from that, we can use those indirect utility functions or those models of preferences in various policy relevant ways. And ones that I'm particularly interested in is the derivation of welfare measures, but also other policy analysis, predicted demand, etc. So the indirect utility function is important given we want to use it in various policy relevant further analyses. And then going backwards, obviously experimental design underpins the indirect utility function, so also very important. Okay, so as you already know, experimental design is a combination of the attributes and levels to create alternatives or profiles, scenarios, but then also the placement of those into choice sets. So the experimental design has key implications for the composition of our indirect utility function, and particularly what type of effects we can estimate. So standard practice in health economics, not so much in other areas, but definitely in health economics, is to use a generic, or traditionally has been to use a generic forced choice experimental design. So for example, you might give two alternatives, present two alternatives to respondents that could be healthcare provider A, healthcare provider B, and then ask them which they want. But the labels A and B carry no meaning. They're generic, and indeed the attributes are generic across the alternatives. So that's pretty much standard, or has been standard practice. So then we're estimating generic effects. We're just getting the effect of the attributes independent of the alternatives that we're presenting. It also, the forced choice nature also has implications for demand analysis and welfare analysis, because here we're forcing folks to choose. We're not allowing them to say, okay, I don't like either of these alternatives, I want to stick with my status quo or current alternative. So I guess that leads on to the next area that's been used in health, is to still stick with a generic design, but to add a status quo. So you present folks with alternative A, alternative B, but then you also let them choose to stay with their current option, to say, I'll stick with my status quo option, whatever that might be. In the example of the healthcare provider, it would be healthcare provider A, B, or no, I'll stick with my current provider. Okay, but here we're still getting generic effects across the attributes, but we can capture the preferences for the hypothetical versus their current or status quo in our modelling. Okay, so that's pretty much standard practice in health. But of course, alternative specific indirect utility functions might be relevant, and we can think of a number of reasons why not all choice problems that are of interest are generic. So I guess 4 examples of why we might not have generic, we might not be interested in generic choice is because the alternatives could be labelled. So, and that itself could carry meaning. You could think of choosing between airlines. It could be that BA, the label BA, carries a very different meaning to the label EasyJet, for example, over and above the attributes that you're showing to folk. And we might want to capture that. Alternatively, some attributes could be available in some options, but not in others. So some goods may have more attributes than other goods, but we may still want to present them within a single choice set. So we might want to have alternative specific effects because of that. Indeed, we could have the same types of attributes, but show different levels on those. And I'm going to give an example of that in my case study. And then even if we had generic attributes in each of the alternatives that we're offering to respondents, it could be that people's sensitivity or their response to those attributes could differ depending on the names of the alternatives that we're presenting. And again, I'll show an example of that. Okay, but before getting on to the real example, going back to our little hypothetical example of healthcare providers, it could be that labelling those alternatives, instead of just saying healthcare provider A or B, we might label them as, say, nurse practitioner and GP. And indeed, those labels could carry meaning. And then we might describe those healthcare providers on a number of attributes, but 2 might be how long you have to wait to see the healthcare provider, and another one might be price. And so here we can think about people's willingness to wait could differ depending on who they're waiting to see. So we might want to allow for an alternative specific or different response to wait time depending on who they're waiting to see or depending on which alternative they're choosing. So we need to think about creating experimental designs that allow for these separate effects for wait time and other attributes as well, linked to each of the 2 types of alternatives. So enter, excuse me, enter L to the MA designs. So these were developed by Jordan and colleagues, and they're used generally in conjunction with labelled experiments, where I've said the labels carry some meaning, and they allow for identification and estimation of these alternative specific effects on the attributes. So if we think of the L being levels, excuse me, and the A is attributes, then usually we think of a full enumeration as L to the A. So here we're just adding in one extra variable, and that's the M, and that captures the dimension for each choice set. So we're saying that our design is dependent on the levels per alternative, but also on how many alternatives you have. So sticking with our healthcare provider example, suppose we just have 2 attributes. We would probably have more, but for simplicity, we'll stick with the price, say having 4 levels, and then also wait time, having 4 levels. So here we have each of the 2 attributes, the A's are 2, each having 4 levels, and we have 2 alternatives. So our L to the MA is 4 raised to the 2 times 2, so 4 to the 4, it's going to give us 256. So all this is doing is saying, let's treat each of the alternatives having individual attribute effects. So we end up with, in this case, double the amount of columns in our design than we would start with if we were thinking of them being generic. So I think one neat advantage of this approach is that instead of sequentially creating our starting design, our profiles, and then sequentially placing them into choice sets in certain ways, and then presenting them to respondents, it does it all simultaneously. So we're creating both our profiles or our alternatives, but we're simultaneously creating our choice sets, so we're the placement of those alternatives into choice sets. So it's doing it in one step, so that's nice and easy. The identification properties are well understood, but the optimality results are not yet in the literature. Okay, so bit of a change of pace. Now looking at the type of choice experiment elicitation task that I use in this presentation. So usually we think of DCEs, and indeed Mandy spoke about these yesterday, as we present alternatives in choice sets and we ask respondents to choose one alternative per choice set. And then they move on to the next alternative. So if we're thinking of the healthcare provider example, they move on to the next one, and then they tell us which of the healthcare providers they prefer. They move on to another choice set, and they keep choosing just best per choice set. What a best-worst choice experiment does is it asks more questions within a choice set. So suppose we had 3 alternatives. In addition to just asking respondents to choose the best alternative in every choice set, we can also ask them to choose the worst. And then we have more preference information because we have a full rank order over those alternatives. We know the best, we know the worst, and by implication we know the one that sits in the middle. So this is best-worst. Choice experiments are one type of best-worst scaling introduced by Louviere and colleagues in the early 90s, but I guess it's fair to say it kind of was introduced, not a lot happened with it, and then lately there's been a real interest in various types of best-worst elicitation tasks, and this is one type. And this is the type that is most closely related to standard DCEs, or standard choice experiments. Okay, so suppose we have a choice set with J alternatives. There's going to be J minus 1 subsets considered by respondents, and we can ask them to make up to J minus 1 choices. So for example, suppose there's 5 alternatives in a choice set. Let's just label them A, B, C, D, E. We can ask respondents to make 4 choices in each choice set. We can say, what's the best alternative out of the 5? And then we can say, okay, out of the 4 that's remaining, what's the worst alternative? And then we can say, out of the 3 that's remaining, what's the best? And then out of the pair that's remaining, what's the worst? And then we get our full rank order. Then we move on to our next choice set. So we're asking, rather than asking more choice sets and more questions per choice, more choice sets with just asking for first best, we ask more questions within a choice set. Okay, so for example, for a given respondent, if A was best, E was worst, B was second best, and D was worst, we would have the full rank order for that individual in that choice set. Okay, so 2 nice properties of best-worst DCEs. As I've mentioned, you get the full preference order, so we have more data. So this gives us nice gains in efficiency when we estimate our models, and that's what I'm going to focus on today. However, if we couple it with optimal design of particular types, it also allows us to estimate models for single individual. And this picks up on what Jordan was talking about in his presentation yesterday. So rather than pooling all our data and estimating a model for our whole sample, and then using various ways to try and account for heterogeneity or differences across our sample, we can take it from the other perspective and say, okay, if we're really interested in heterogeneity, why not estimate a model per person and then aggregate over them in various ways to get to our measures of central tendency. But then we can look at our distribution of what are the heterogeneity we're interested in, if it's preference heterogeneity or variance heterogeneity, by empirically characterising that distribution. So we get more information. Okay, but as I said, I'll focus on the first. So I've said that we use these experiments and we get this rank order. So I think it's not surprising that one approach would be to estimate a rank order logit. And as I guess many of you would know, a rank order logit assumes that respondents, or that we've arrived at this rank by choosing best. If we stick with the example of the 5 alternatives, A, B, C, D, E, a rank order logit, when you estimate the model, is assuming that the respondent chose best from 5, and then out of the 4 that were left over, chose best from 4, best from 3, and best from 2. So it assumes that we're making the best, that respondents are choosing best from successively smaller subsets of those alternatives. But of course we know that's not how we get our data in a best-worst choice experiment. We ask for best, and then we ask for worst. We ask for best, and then we ask for worst, and so on. We don't ask best, 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 best. I was using the rank order logit at the time and felt slightly uncomfortable with that. I was modelling the data in a way that they hadn't been generated. So the objective was to see if we could model those data, accounting for the sequential best-worst way in which we had elicited that data, accounting for the choice of best followed by worst, best and worst. Okay, so what the what we've called the sequential best-worst M&L model does is it models the probability of a best-worst preference order as the product of j minus 1 choices that respondents make in choice sets of size j. So it looks like a rank-ordered logit in that, but it's actually modelling the data in the way they were generated. So the first one's just our M&L. You can think of this just our C logit for choice of best from all 5. This is our M&L choice of worst from the remaining 4, choice of best from the remaining 3, choice of worst from the remaining 2. So the key things where it differs from rank order logit, obviously the first choice is identical, but then the choices made in the smaller subsets differ. So we're choosing worst in the second and final places, and what they're choosing from is obviously differing, the subsets. So key assumptions in using this model is that each of these obviously following M&L and all the assumptions that come with that. And then also that I've assumed that the utility of choosing an alternative as worst is equal to the negative utility of choosing that alternative as best. And actually, strictly speaking, it's the deterministic or systematic part of utility that's we're making an assumption over, not the random component. So I think I've said all that. Testing that assumption, it holds very well in this data set. It's tractable, and it's also, we've used it to estimate pooled models, and I'll show you one example in this data set, but we've also used it in another data set looking at preferences over treatment for cardiac arrest to estimate a model per person and then aggregate over those. Okay, so now getting on to the empirical study where we demonstrate some of these approaches. We were looking at preferences for drinking water in Sydney, Australia, and drinking water in the home. So a couple of issues with regard to drinking water. Well, obviously safe drinking water is fundamental to good public health. There's health risks, small health risks associated with both untreated drinking water. If we don't treat our drinking water, there's the chance of adverse health effects. And then if we do treat our drinking water, there's also a very small chance of adverse health effects. In addition, we can either choose as society to add fluoride to our drinking water or not, and across the world different decisions are made about adding fluoride to public drinking water facilities. And then also we've observed a substitution from tap water to tap plus filtering that tap water in some way, and also to bottled water. So these are some of the background issues to this study. So focusing a little bit on the health risks, if we don't treat our tap water, I think many of you will know that it can be hazardous to human health because of these microorganisms that are potentially in the water. And common examples are Cryptosporidium or Giardia. There's other types of microbial illnesses that can eventuate. So for that reason, most, indeed all developed societies clean and filter their water using various methods to remove those microorganisms to prevent any type of microbial illness. And in Australia, chlorine's the most widely used disinfectant. So we chlorinate our water, and then there's that produces disinfection byproducts, and the big example of that is trihalomethanes. And there's linked to that, there's a possible association. So a causation hasn't been found, but there's definitely an association between long-term exposure to these trihalomethanes and various types of cancer, but particularly bladder cancer. And so for that reason, there's been a lot of work done on alternative ways to clean and filter our water, in addition to adding chlorine, to then doing additional things to get rid of these trihalomethanes. So one example is carbon filtration, but there's others. Okay, so we're dealing with a known risk of if we don't treat our water, people can become sick from microbial illness. And then on the other hand, we're faced with this possible smaller risk if we do treat our water, that we also can have some adverse health effects. So there's trade-offs across the various risks. So I guess I've just said that the immediate risk of microbial illness, traded off against a possible small future risk of bladder cancer in particular. But then in addition, whether or not we add fluoride to our water, we can have different health outcomes in terms of dental and oral health outcomes. There's good evidence to show we add fluoride to our water and we have better oral health outcomes versus if we don't. And then within each of these types of risks, so the microbial illness on the one hand and the bladder cancer, we obviously have two types of risks within each. We have the risk of morbidity, the risk of becoming unwell, and then you have the risk or chance of dying. So we've actually got 4 types of risk in this study. Okay, so some previous work. Bateman et al. Looked at drinking water, but they only looked at taste and aesthetics. So whether it was cloudy, what it tasted like, but nothing linked to health risks or fluoride or indeed types of water. They just looked at tap. Mitchell and Carson looked at trihalomethanes and people's willingness to pay using a different method. They used a direct contingent valuation approach, and they looked at people's willingness to pay to reduce the risk of these trihalomethanes and the risk of cancer from drinking water. And then Adamowicz et al. Also investigated trade-offs between these microbial illness and bladder cancer, and they focused in particular on tap water. Okay, so what our study does is it's obviously building on this earlier work. We have a broader inclusion of health risks with both the microbial illness, the bladder cancer, but then also the issues around oral health with adding or not adding fluoride. And then we were very interested in these preferences and potential substitution across different types of drinking water. So tap water, tap with a filter, and bottled water. And so that led us down the track of using, because they were clearly labelled, tap water is a label that differs from bottled water, even if we have the same attributes and describing those alternatives. So we have a labelled experiment, and we also use this best-worst data collection and an analytical approach. Okay, so our choice context was drinking water in the home in Sydney, Australia, and we presented respondents with a choice between 4 alternatives in each choice set. We described to them the current status quo alternative, which is their current tap water that comes into their home, and we know the attributes and levels on that, and that stayed constant in every choice set. So they could always choose to stick with their current tap water. And then we presented them with 3 hypothetical alternatives that we generated throughout using our experimental design. And we had a hypothetical tap water that we described to them as arising from different forms of treatment. We also had a hypothetical tap water with an added home filtration. And then we had a hypothetical bottled water alternative. So people could choose to not drink any of the tap waters and to choose bottled water, as indeed some people do in the real world. And then because we had 4 alternatives, we asked them what was the best or the one they most preferred. And then out of the remaining 3, we said, what's the one you least prefer? And then out of the remaining pair, we said, what's the one you most prefer out of those 2? So we get a full rank order over the alternatives in every choice set. And we used an online panel to collect our data, representative of the population in Sydney. And we had just over 500 respondents in our sample. So we generated our attributes and levels from the literature, but then in addition from focus groups with respondents, and then also we piloted that to make sure that we had the right attributes, the right levels, and then indeed that we were describing them in ways that respondents understood. And we spent a lot of time focusing on the risk attributes, because we know that there's folks have difficulty in understanding risk, and then we were asking for trade-offs across various types of risk. So both in the qualitative work that we used to develop our survey, but then also within the survey, we spend quite a lot of time on the risk attributes. So we have 6 attributes. We have 4 risk attributes, each with 4 levels. So risk of microbial illness, risk of then dying from that illness, risk of bladder cancer, and the risk of dying from bladder cancer, price, and then added fluoride, whether or not fluoride was added, yes or no. And then the price was, the levels were alternative specific. So each alternative had these same attributes, but the price attribute differed across alternatives. So the actual price of drinking water in Sydney at the time was in the fraction of cents per litre for tap water. And then adding the home filtration was slightly more, but we're still talking cents. But then the price per litre of bottled water, we're now talking in dollars. So there's a big magnitude of difference across our price attributes. So we had to account for that in our experimental design. And then other possible drivers of choice, taste and aesthetics, we held them constant in every choice set. So we asked respondents to assume that they were the same across the alternatives. Okay, so we wanted to estimate alternative-specific indirect utility functions. As I said, standard practice in health economics has been to just have one utility function, whereas here we wanted to allow utility to differ depending on whether it was tap and filter, or bottled water. And then our status quo we set to 0, obviously to allow for identification. And now, of course, this isn't uncommon in other areas where DCEs are used. You can think of transport, where you could replace that with, you would have utility linked to bus, car, train, for example. So it's certainly been used in other settings, but it's not particularly common in health. Okay, so our experimental design, we went down the track of using a L to the MA design because we had these labels, and indeed we had an alternative specific price attribute. And then in addition, we could have an alternative specific response to the other attributes depending on which alternative they were linked to. So we wanted to make all our attributes alternative specific. So we had 5 attributes at 4 levels, and we had 3 hypothetical alternatives. And we had 1 attribute at 2 levels, again, across the 3 alternatives. So we had 4 to the 15 times 2 to the 3. So we created a fractional factorial L to the MA by hand. So I started with an orthogonal array of containing 17 16 level attributes. And from that, I used 3 of them to generate 6 attributes that were involved in the interactions, and then used I think it was another 9 for the rest of the 4 level attributes, and then I used one of the columns to create my 3 2-level attributes, and then I deleted the rest of the columns. And then I blocked that into 16 blocks of 16 choice sets per block, and did that multiple times to choose the one based on such that each of the versions themselves were orthogonal, and we had level balance across those. The design allowed for all main effects across each of the alternatives, and 3 two-way interactions. So 1 per alternative, and the interaction that I focused on was the interaction between cancer and cancer death. Okay, so the modelling, this is work in progress, but so far started at, I guess the most common starting place was just a conditional logit with robust standard errors, and I tested for whether these effects were alternative specific. So does the response to risk differ depending on whether people are choosing bottled water versus tap water? And then also tested for various functional forms. I then went on and estimated the sequential best worst, M&L, using the same structure, and then compared them. And as I've said, this is preliminary and ongoing. We've got lots more analyses of these data to do, accounting for various types of heterogeneity. Okay, so collected lots of information about people's revealed preferences in the survey. So we asked lots of questions about what they drank at home, why they drank it, concerns about health effects, etc. But in terms of what they most drank at home, most people drank tap water at home. I guess the next biggest group was to drink tap water, but they filter at home. Some people boiled their tap water, and then the rest either drank bottled water, and we differentiated between whether that was delivered, the big bottles, or whether they bought it in supermarkets, and then a very small percent used or drank rainwater that they collected themselves. Okay, so the results. So here I've just summarised the results for you. Preferences, there was a clear preference for tap water over, or the various types of tap water over the bottled water alternatives. So we have in our models alternative specific constants to capture the effect holding all the attributes constant. And that suggests that the status quo was preferred to the hypothetical tap water, which was preferred to the hypothetical tap and filter, which was preferred to the bottled water. And indeed that reflects what people told us they actually do at home. And then using various tests, preferences for the risk attributes were actually generic across the alternatives. So then we collapsed our model and just have 4 risk effects rather than 4 by 3 alternative risk effects. Price sensitivity did differ across alternatives, and that's not surprising given that the levels differed across alternatives, but also fluoride, whether people wanted fluoride added to their bottled water, tap water, or tap and filter also differed. Okay, so the probability of choosing each of the drinking water alternatives increased, not surprisingly, with lower risk of either morbidity or mortality, with lower price, and whether fluoride was added. That was in particular in tap water. Risk effects were all negative and significant. Price effects were all negative and significant. And people preferred fluoride on their tap and filter, and they didn't care about adding fluoride to the bottled water. The cancer by cancer death interaction wasn't significant in this model. This is just the C-Logit results. And then looking at some preliminary just marginal rates of substitution to look at how people trade off the various risk attributes. Risk for mortality was more important than morbidity, and I guess that's not surprising. And the risk of cancer was also more important than for microbial illness. So for a given risk level, people felt more strongly about that, and it affected their choices more strongly if it was linked to cancer versus microbes. And I guess that's not surprising and can link into a whole literature on what's called dread risk, so the different ways of dying seems to matter to people. Okay, I then have also estimated the models using the sequential best worst M&L. So the C-Logit just used the first best alternative in each choice set. Now I'm using the full rank order over the alternatives, using the sequential best worst M&L that I showed before. And the results had the same interpretation as the C-Logit. The exceptions were that now fluoride on bottled water was significant and positive. So people do, in this analysis, it suggests that folks do want fluoride added to bottled water. Cancer by cancer death interaction was now significant and negative, as we would expect. And not surprisingly, we have smaller standard errors because we have much more data that we're using to estimate the model. And we have generally smaller coefficients, and which is suggestive of a scale effect, that we have lower scale, higher variance in the sequential data. And so we're yet to test explicitly for that, but I guess one way to think about this is when we plot the results of the sequential model against the C-Logit, they're proportional but with a slope, so that's suggesting that we have more variability in our sequential data, but we will get on and formally test for that. Okay, so the gains from using all this extra data from our best worst task, we have these lower standard errors compared to our first choice analysis, and that's reflecting the gains that we're getting in the efficiency, not surprising. But we also got more significant effects. So now the interaction became significant and the fluoride effect also became significant, whereas it wasn't in our first analysis of just the first choice per alternative. Okay, so to sum up, we've used L to the MA design to allow for these alternative effects rather than assuming that all attribute effects are generic. These are just preliminary results. We found that we have some alternative specific effects on price and fluoride, but indeed the risk effects were generic across alternatives. The results so far in terms of people's preferences for drinking water suggest that people prefer tap over other forms of drinking water, and this also is reflected by their actual choices they're making in their home. The response to risk was generic across the alternatives, but they generally prefer lower risk, but that differed depending on the type of risk. So people cared more about the mortality risk than the morbidity risk, as we would expect, and they cared more about the cancer-related risk than the microbe-related risk. And they wanted fluoride added to their water. So we've demonstrated the use of best worst choice experiment and this new sequential M&L approach, and it's just work in progress, so lots more to do. Thank you.
All right, we have plenty of time for questions, and perhaps may I start with one question regarding the picture you showed towards the end,
Yeah.
the plot of the utility values. I mean, does that line actually pass through the origin? Because I mean that would be required by the utility theory, right?
Yeah, it is. Well, I would have to check. It looks like it is here, but I could definitely check for sure. Yeah.
Yeah. Other questions? Ben?
I'm not completely familiar with this area, but the conditional logic module, you were just fitting first preferences?
Yes. So I just utilised the choice of best from the 4 alternatives, and I ignored the extra preference information that we used in
Then if you move on to the full ranking model,
the choice.
are the two models consistent in that if you took the full ranking model and worked out the probabilities of all the first preferences, are the two models, is that
Yes,
the same?
well, yes, because it nests the C logic. Yeah.
Brett?
Doug, you said something about the coefficients for the sequential best worst being smaller than the other ones. That's a bit disturbing. Does that say something about the probabilities of choice then?
So they're proportional up to scale. So what it's suggestive of, but we've got a test for it, is that we have lower scale in our sequential model, which we know that all limited dependent variable models that confound the betas with the error variance, and our scale is just the inverse of our error variance. So that's telling us that we have higher variability in our sequential best worst data. So I don't think it's disturbing, but I think it's reflective.
Simply because you're adding all of that extra data.
There's much more to explain.
Solutions, so there's more variability across all of the interior than there is on the two extremes.
But if you're going to look at a difference between two possible alternatives, then the probability of choosing one and just using the one model and using the coefficients would be different than the probability of the other. That's what bothers me.
That's, well, it not only bothers you, it bothers about 99% of the discipline. And the reason it does is this is a classic scale effect. So, for example, if you think about the problem of forecasting new products, that's inherently the problem. You have to know the scale of the choices in the new environment relative to the environment in which you estimated the model. It's not obvious how you do that.
I have another question. I mean, quite early in your presentation, you mentioned that the optimality properties of the LMA designs have not been published. I'm not sure whether you're talking about statistical optimality here, because I think in the context of generic choice experiments, those designs are not optimal. Is that?
So I don't actually know much about the optimality properties at all of the ELTA and the MA, and there's no discussion of it in the literature. My understanding is that Leonie Burgess has been looking at these, but I'm not sure where she's at with
We understand there's a proof, but we haven't seen it. So there apparently is a formal proof now that L to the MA designs are optimally efficient. But no one in my research center has seen this proof.
But in which context? In the context of generic?
No, in the context of alternative specific problems.
For which model?
Conditional logic.
Under zero priors.
Have you seen the proof?
No, but
No.
Dennis.
it's the only way it could
Not sure
possibly
this
be.
make any sense at all. It's a very naive idea. In political science, sometimes you worry about the worst, not the best. So if I reverse this whole process reversely, I do worst best model, for example, would that give you symmetric result or?
Well, this is assuming, so I guess there's two ways to answer that. Is we can analyse that. We could analyse going worst, best, and then both the numerator and denominator of our probability and our likelihood change. And that would be an obvious test to do to answer that question. And I haven't done that as yet in these data. But what I have done is estimated a model on best, and then I've estimated a model on worst, and then I've looked at whether they're symmetric. And indeed they are. So my coefficients on each of those are of the opposite sign, as we would hope, and indeed in absolute value are very close.
Well,
So-
my feeling is the whole process is not symmetric in a way that you seems to put more weight on one end, not the other end. If you worry about
Why?
best,
Why does it put more weight?
well, from data collection, ever since data collection till analysis, I think it's, well, I can talk about it, but I think people would, when you worry more concerned best or more concerned worse, your ranking may be a little bit in the
So
middle.
you think if respondents are approaching this thinking that what they really care about is the worst, yeah, perhaps that the way we've asked it puts equal weight on in that we ask best first, that could put more weight on best, but it's also a more familiar choice for them, so I think it makes sense to start with best. Then we flip to worst, then we ask best and worst until we have a full ordering. But if respondents are coming to this thinking, I really care most about avoiding the worst thing, and I think that's going to be context specific, but you can certainly think of contexts. Perhaps a risk context might be one of those, but I think that depends on how respondents are approaching it, and I guess that's an empirical question, and perhaps qualitative analysis alongside these might help inform that. Yeah, but thank you. I think let's think more about it.
It's also possible that the error variance associated with each of these choices is different, as
Yes.
well as the depth in the ranking process, the error variance can be different.
And indeed,
That's-
yeah, I haven't presented, but preliminary work looking at error variance, it does suggest that it's different. Particularly on the interior. The exterior, they're pretty similar, but when you start to move into the interior.
That's consistent with a lot of other papers looking at.
Yeah. And and indeed the papers looking at rank order as well. Yeah.
But is it not possible to show that the model for best and model for worst are equivalent if you do an inversion?
Yeah. Yeah.
So you would expect the parameter estimates to be exactly consistent.
Up to scale.
Up to scale. Yeah. And I guess the first step in doing that is to estimate a separate model on best and separate on worst. And I've done that, and indeed they are consistent and symmetric. But the next thing is to estimate the other way, going from worst best to test that.
Perhaps one last question. I mean, you mentioned this huge price difference between bottles and tap water, and
Yeah.
that this had to be taken into account when designing the study. Is it possible to describe in a few words how exactly that was taken into account?
Well, it's taken into account by allowing for an alternative specific attribute on each of those. So it's in a sense, well, I have 3 price attributes. I have price for tap water, I have price for tap and filter, and I have price for bottled water. So they're treated in the design as separate, independent attributes and separate columns.
Okay, so let's thank Emily again.